Uh, Alright guys, just give me 1 second. Let me quickly check if I'm online. Okay. So good evening everyone, and good evening Anjali. So before we begin, today we are going to learn about Biot-Savart law. Okay, and before we begin, if you're there online, just tell me if you can hear me and if my audio is clear as well. And okay, right. And my name is Mohana. I'm a physics educator here at Unacademy, and I'm a plus verified educator. So if you can follow me through the Telegram channel, and this is my Telegram channel link, and also this is the common ICSE and ISE board Telegram channel. You can follow this channel as well. Alright, so today we are going to learn about Biot-Savart law. So if you generally see, right, let's take a bar magnet. Okay, so if you take a bar magnet, right, so there is going to be field lines everywhere around this bar magnet, right? Outside it's going to be from the north to the south pole. Inside the bar magnet, the field lines is going to go from south to north, right? So it feels so if you generally look at a bar magnet and the field around it, it forms a closed loop around the magnet, right? Similarly, if you take a current carrying conductor, that is, for example, if you have a charge which is moving, which is nothing but a moving charge is nothing but current, right? So let's say you have a wire, okay, and there is current flowing through this wire. Okay, now what was observed was, when there is a charges which are in motion, when charges are in motion, we basically say that is nothing but current, right? So when there is current passing through a conductor, then just like how we see magnetic field lines around a bar magnet, we observe field lines around this conductor as well. Okay, so this is nothing but, and over here, Biot and Savart in the year around 1820s, okay, they tried to derive an expression for a wire that is carrying current, right? Because this wire carrying current produces magnetic field, right? So they try to give a expression for that magnetic field. Okay, so before we go ahead, we have to understand one term over here, that is, let's take a wire, and there is a current passing through this wire. Now what I can say is, every part of this wire produces magnetic field, right? So if you see over here, there would be magnetic field lines. If you see around this part also, there's magnetic field lines. Everywhere around this wire, there would be a magnetic field line. Okay, what is the source over here? You have a charge that is basically in motion, right? A moving charge is producing this magnetic field. So this entire length of the wire that we have, what we can say, we can actually divide it into, right? We can say these are made out of small amount elements over here, right? This entire wire, we can say they are made out of small elements. So you take one small part over here, okay, let's say this entire length is L. The small length over here, I can call it as DL. Okay, this entire wire is made out of such small DL amount of elements of wire. Now if the total current passing through the conductor, for example, let's say current through this is 2 amps, then through this element DL also there would be a current flowing in through the small element also, right? The current flowing through this element also will be 2 amps. Okay, now so this element, the small element of a wire that we are taking, because of the small element of wire, we are seeing what is the magnetic field lines produced because of this. This is basically called as the small element is called as current element. Okay, and if you see, it's a vector quantity. Okay, and since it's a vector quantity, we have to give it a direction. So whatever is the direction of current in the circuit, this element DL has the same direction as the current in the circuit. Okay, all right. Now let's see what is basically Biot-Savart law. Now to understand Biot-Savart law, what we are going to see, we are doing a very simple thing, that is, we are taking a wire and this wire is producing magnetic field. Biot-Savart law just gives you that expression for magnetic field. So for that, let's take a wire. Okay, let's say the entire length of the wire is basically XY, out of which what we are seeing, this wire is made out of small elements DL. Okay, this is what we are going to consider. We are going to say this entire wire is made out of small current elements. Okay, now we are this in this wire, let's say there is a current I flowing through it. Now we are going to consider a small element, that is a very small segment of this wire. Okay, the entire length of the wire could be L. A small segment of this particular length, we will take it as DL. Okay, now this is the small segment DL. Now when current flows through this part of the wire, there would be a magnetic field produced. When there is passing through this part, there would be magnetic field produced. Everywhere throughout this wire there would be a magnetic field line. Okay, so what we are interested in, we are not going to find what is the total magnetic field line. What we are going to do, we are going to take a very small segment of this wire. Okay, that is nothing but this element DL, and we are going to say because of this element DL, well, let's choose a point. Let's choose somewhere around here. Okay, somewhere some distance from the wire. Okay, let's mark this point over here. Let's say at this point over here. Okay, we want to find what is the magnetic field line. Okay, now once again, point to be noticed is from this current element, this point, the distance point P that we have chosen. Okay, this particular point we have chosen is at a distance of about let's say the distance is basically R. Okay, so this is nothing but the position vector, so we can give it as R vector. Now if you see at this point P, we want to find what is the magnetic field. So between this current element DL that you have taken and this R vector over here, there is an angle dependence, okay, of about theta. Now, okay, so from here we can say we are not bothered about what is the magnetic field because of the entire length of the wire. We are just saying we are taking a very small segment of the wire, and through the small segment of the wire there is a current passing through. Because of this current, what is the magnetic field at point P? Okay, so that magnetic field will be nothing but dB over here. Okay, we just want to find what is this magnetic field dB, this expression for this magnetic field. Okay, so according to Biot-Savart law, what would be the magnitude? Okay, what would be the magnitude of this particular value was basically given by, okay, according to Biot-Savart law, we can see that this magnetic field dB we have over here is directly proportional to the current passing through the wire. Okay, that is, let's say increase the current passing through the wire. Okay, let's say now the current is around 2 amps, make it 4 amps. Current of magnetic field strength magnitude over here will increase. For example, let's say magnetic field strength is 0.1 unit. Okay, that will actually increase. Okay, now the next one is obviously the next dependent quantity is the current element DL. Okay, so now this magnetic field, the magnitude of the magnetic field, if you take, it is again directly proportional to the current element DL over here. That is, if you increase the length of the element, for example, let's say this wire is of 100 meters, out of which the DL could be somewhere around, for example, 0.1, you're taking 0.1 centimeters as that small wire to be the current element. Now increase it, make it 1 centimeter. What will happen? Obviously current flowing through that circuit is more, current flowing through that element increases. Right, from taking a smaller element, you've chosen let's say you've chosen a much bigger element. Now current through the through this particular element has increased. If current flowing through this increases, what happens? There would be more magnetic field lines, which means magnitude, the value of magnetic field over the magnetic field line. Okay, sorry, the magnitude of magnetic field line will be again more. Now other than this, if you see, this particular magnetic field is again proportional to the sign of the angle between this current element DL and the position vector R. Okay, now other than this, okay, now one more point to be noticed is that dB, okay, is inversely proportional to the square of the distance from the point to the current element. Okay, so from here to here, what is the distance? It is dB is inversely proportional. Now if you put all of these together, the equation you will get is dB is proportional to what was it proportional to? This was proportional to the current flowing through the circuit, right, and the current element DL, and there is a sign of the angle dependence between the DL and the position vector R, the whole of this divided by, okay, R square. Now we want to remove this proportionality sign, so we introduce a constant K Okay, then we have I dl sine theta divided by r square. Okay, now this constant k is nothing but called as the permeability of this k is nothing but has a value of mu naught divided by 4 pi. Okay, so this is nothing but it just over here mu naught is nothing but permeability of this free space, meaning this talks about the medium that exists between the current element, that is a wire that is carrying current, and the magnetic field line. What is the region like in between? Is it a vacuum? Is it air in between? Okay, or is it some other state? Or is the magnetic field line, for example, let's say the current carrying element is inside water. Okay, how would the magnetic field line change? So this mu naught depends on that particular medium, that is where this particular wire is present. Okay, now this mu naught over here, okay, this mu naught over here has another value, that is mu naught will be nothing but mu naught is nothing but equal to 4 pi into 10 to the power of minus 7, okay, Tesla meter ampere inverse 1. Okay, so if you substitute all of this in the equation, we will, instead of k also, if you substitute all of it, you will get dB is equal to mu naught divided by 4 pi I dl sine theta divided by r, divided by, I am really sorry, okay, this will be r square. Okay, now this is basically magnetic field. So this equation gives us what is the magnitude? What is the magnitude of the magnetic field at this point P over here? Okay, but magnetic field, if you see, is a vector quantity. So how can we write this as a vector form? Very simple. Let's see what is the field line like. Okay, we just saw that is dB was equal to, we saw it is nothing but mu naught divided by 4 pi I dl sine theta divided by r square, right? So what we would do right now is, let's multiply, okay, let's multiply and divide, okay, let's multiply and divide by r. So how would this change the equation? Is very simple. You will have mu naught divided by 4 pi I into, okay, then you will have I into dl into r sine theta, okay, this is one quantity, divided by r cube over here. Now r dl sine theta, this is nothing but, if you've seen, this is nothing but the cross product, right? Sine theta basically gives us the cross product. So we can take mu naught I divided by 4 pi dl r into sine theta. This can be expressed as dl, okay, cross r vector, okay, divided by r cube, right? So this gives you the vector form of the magnetic field. Now, very simple, why not write this as r cross dot dl, right? Next question is, why not write this as r cross dot dl? This is very simple. We have to consider, because it's a cross product, we have to consider the direction in which the vector moves, right? So here, if you want to find the direction of the magnetic field, we have to consider how this dl vector and r vector, which moves towards which. Okay, so if you see over here, you can use the right hand screw rule or the right hand thumb rule, but the easiest one is right hand thumb rule. If you see, make sure that because it's again a vector product, what we can do is think of dl, the element dl, moving towards r over here. Okay, so we have dl and it's moving towards r. So the curls of the finger tells us in which direction the two vectors are moving, and my thumb will basically point at the direction of the new vector, that is the direction of the magnetic field. So my thumb is pointing downwards, which means at this point P, okay, the magnetic field lines will be basically passing into the screen. Okay, the magnetic field line will be passing into the screen at the point P over here. Okay, so this is something where you would have learnt in your grade 11 itself, right? So this sums up your Biot-Savart law. So using this expression, you can actually find what is the magnetic field that is produced by a current carrying conductor. Okay, now very simple. What do you think? If you know the answer, you can give it in the chat box. What do you think is the SI unit of magnetic field? What do you think is what is the SI unit of magnetic field? Okay, so we have Newton per Coulomb, Tesla, Weber and Maxwell, right? So here the answer is nothing but Tesla. Okay, so the unit of magnetic field, if you see, it's named after the scientist Nicholas Tesla. Okay, now very simple. If you take the Biot-Savart law, we have nothing but dB is equal to mu naught divided by 4 pi. Okay, then we know this is nothing but I dl sine theta divided by r square. Okay, so here let's take an assumption. Okay, let's say that current, we have taken a wire, okay, and let's say the wire length is about 1 meter. Okay, so this dl element is about 1 meter, and let's say through this 1 meter of wire 1 amps of current is flowing through. Okay, now let's take the distance. Okay, so we have 1 meter long wire, and the current flowing through this I is also equal to I is also equal to what? 1 amps, right? Now from here, okay, we want to go theta equal to 90 degrees. I'll explain why we are taking theta equal to 90 degrees. Okay, so let's say theta equal to 90 degrees means sin theta will become 1. Okay, so from here, okay, 90 degree from here means from the wire about a distance of 1 meter. Okay, let's make r is also equal to 1 meter. R is equal to 1 meter again. Okay, so from this wire over here, we move a distance of 1 meter, and at this point P we want to find what is the magnetic field line. Okay, now the angle over here we are seeing is between the current element dl and the distance that we are moving, dl and r. If you see the angle dependence between them is actually 90 degrees. Now from here, if you see, if you substitute all of this in the equation, so we'll get dB is equal to mu naught is nothing but 4 pi into 10 to the power of minus 7 divided by 4 pi. Okay, I dl sine theta, sorry, all of this is basically 1, right? So you will have 1 amps into 1 meter wire, right, into sine of 90 degrees, so that is 1 divided by 1 square. So over here what we get, this dB will be equal to 10 to the power of minus 7 Tesla. Okay, so from here we can get 1 Tesla. 1 Tesla is what? 10 to the power of 7 dB. So 1 Tesla, because magnetic field unit is nothing but Tesla. Okay, so this is nothing but so many Teslas, right? So from here what we get, 1 Tesla is 10 to the power of 7 times the magnetic field produced by a current carrying wire, okay, of length 1 meter, carrying current of 1 ampere through it. And if you see the magnetic field line is at, magnetic field strength is 1 Tesla, okay, that is if the distance between the current carrying element and the point we have chosen is 1 meter from it. Okay, so 1 Tesla is 10 to the power of 7 times the magnetic field produced by a conducting wire of length 1 meter carrying current of 1 ampere, okay, and at a distance of 1 meter from it, and if you see it is perpendicular to it. Okay, now before we end the class, I want to notice, we want to look at one more point also. Okay, when can you get maximum magnetic field and when can you get minimum magnetic field? Okay, that is, for example, let's take this angle theta to be 0, which means we want to find what is the magnetic field around the point somewhere over here. Okay, then what will happen? The current element or the R also will be somewhere around this point. Because of this element, current R will also be around this point, right? So dl and R are both in the same direction. Then what will happen to the angle theta here? Theta will become 0. If theta becomes 0, sine of theta, okay, 0 degrees is nothing but 0. Which means, okay, what we get, okay, which means the magnetic field dB over here, if this angle becomes 0, what we'll get, this dB itself will become 0. So what we see over here, the magnetic field is 0, okay, if you choose the point that is along the axis, if you choose a point along the axis of the current element, if you're choosing any point along the axis of the current element, then what will happen? The magnetic field line is basically 0. But let's say same thing, now we will end up taking theta to be like in the earlier case, we will end up taking this, probably let's say this theta is equal to 90 degrees. That is, this point we are taking is perpendicular to the current element over here. Then what would happen? Then sine of 90 is 1. then you will get this dB is equal to mu naught divided by 4 pi I dl divided by r square. This will give you a maximum magnetic field lines. So from here we can say the magnetic field because of this current carrying element is maximum. Okay, if you take a point that is perpendicular to its axis over here, if you go perpendicular, that is as the angle become 90, then you get maximum magnetic field. So before we end the class, so this is all about Biot-Savart law. Now there are different applications for Biot-Savart law. We are not going to do that in today's class. Okay, but before we end the class, let's do one numerical. Okay, so very simple. If you know the answer for this, you can give it in the chat box. Okay, so let's see. A wire placed along north-south direction carries a current of 16 amps from south to north. Okay, find the magnetic field due to a 2 cm piece of wire at a point 400 cm northeast from the piece of wire. Okay, very simple. Let's say we have a let's first say let's say this is our directions, right? So what we have is, let's say this is north south. We know east and west, we don't have to. Again we have east west, right? What the question says, a wire is placed along the north south direction. So we have a wire placed along the north south direction over here. Okay, and if you see the current that is flowing through this wire, if you see it, the current flowing through the wire is from south to north. That is, it flows from south to north in this direction. This is the current. This is the direction of the current. Okay, so we have a wire that is placed at north-south direction, that is placed along north-south, right? And the current through this is from south to north. Okay, and this current is nothing but 16 amps. Now, if you see, we want to find a magnetic field. Okay, due to this 2 cm piece of wire. Okay, at some point 400 degrees northwest. Okay, so we have, this is northeast, and we know this is east, and this is west. So if you go northwest point is somewhere around here, right? So this point from here, from this current element, if you go 45 degrees over here, this is basically your I'm sorry, just a second, right? So this is basically towards the east direction, right? So this is basically your east and this is west. So from northeast over here, if you go 400 centimeters, okay, so this R over here is 400 centimeters, and if you see, we want to find what is the magnetic field line at this point over here, that is dB over here. Okay, now the length of the wire over here, this length of this element is given as, that is, this is dl. This is actually given as 2 centimeters. Okay, now very simple, you need one more quantity, that is the angle. Why? If you want to find dB, you need to know mu naught divided by 4 pi, okay, I dl sin theta divided by r square. So we know what is I, current through it, right? We know what is dl, we know what is r also, and r also, but we want to know the angle. See, this entire angle north to east is basically 90 degrees. Okay, so this angle over here would become, northeast means very simple, this angle would be around half of it, right? Northeast means it's around half of this angle, so this will be around 45 degrees. So theta, we got the theta value also to be 45 degrees. Now all we have to do is just substitute here and try to solve. That is very simple. What is mu naught? This is nothing but 4 pi into 10 to the power of minus 7 divided by 4 pi. Okay, what is current is 16 amps into dl. dl is given it as 2 centimeters. 2 centimeters is nothing but 2 into 10 to the power of minus 2 meters. Okay, so dl over here is nothing but, okay, so dl over here is nothing but 2 into 10 to the power of minus 2 meters. Okay, convert it. So this will be 2 into 10 to the power of minus 2 meters into sine of angle is nothing but theta over here is 45 degrees, right? So sine of 45 degrees divided by r. What is r over here? R is given as 400 centimeters, which is nothing but 4 meters. Okay, so r square will become 4 square. So very simple over here. Okay, very simple over here. Let's see, this cancels, so all you will have is 10 to the power of minus 7 into 4 square is 16, so 16 and 16 cancels, all you will have is 2, okay, into 10 to the power of minus 2 Okay, and if you see, one more quantity is sine 45. Okay, sine 45 degrees. Sine 45 degrees is nothing but 1 by root 2. Okay, so this gives you what, let me see, this gives us, let me write this 2 as root 2 times root 2 divided by root 2. Okay, 2 I am writing it as root 2 times root 2. So 4 square over here is nothing but, this value is nothing but 16. So these two numbers cancels, these two cancels, 4 pi cancels, and this is sine 45 is 1 by root 2, and 2 over here I can write it as root 2 times root 2 into 10 to the power of minus 7 and minus 2 minus 9. Root 2 cancels, then all we get, magnetic field at this point dB is nothing but root 2 into 10 to the power of minus 9 Tesla. Okay, root 2 has a value of 1.414, right, which is nothing but, in this case, if you see, root 2 has a value of 1.414 into 10 to the power of minus 9 Tesla. To round it up, we get 1.4 into 10 to the power of minus 9 Tesla. Okay, this gives us what is the magnetic field at this point over here. Very simple. What will be the direction? What do you think will be the direction of the magnetic field here? Very simple. Think of this wire. Take from the element dl. Okay, from the element dl, go towards r. So from the element dl, go towards r. The direction of the thumb, if you see, it's pointing downwards. It means in this case it will be into the screen over here. Okay, so this gives us the direction of the magnetic field. So with this note, I am coming towards the end of today's class. So there are several applications based on Biot-Savart law. So you can go down to the description box. There would be link to the upcoming special classes that happens on the Unacademy platform. Again, those are completely free classes. So you will see the class title as magnetism and Biot-Savart law and ampere circuital law. So you can enroll for those classes, and we will try, and we are going to learn about the application of Biot-Savart law with numericals, and also what is ampere circuital law and its application in the upcoming classes. Okay, so with this note, we are towards the end of today's class. So if you like the class, please share it among your friends. Do subscribe to the channel, and other than this, there is an ISE and ICSE Masters channel. So do subscribe to that channel as well, and click on the bell icon. So before any class goes live, you will get the notification. Now, other than the magnetism lecture series I talked about, on the platform there is also free free classes for special classes for ray optics also. Okay, so you can enroll for that also. So see you all in the next class. Bye.